So hopefully everybody did the exam. That was due yesterday, but when I was looking at grades, they were really good. I mean, the average was in the low 80s. So, I mean, I think everyone's understanding chapter 1, which is good because we're going to be, we're going to be using all that stuff throughout the next several chapters. So this week, you have just the 2 assignments due for the whole week, and they're due on Sunday. So for chapter 1, notice we have 3 different homework assignments for chapter 1. That's because we spent a lot of time on chapter 1 to make sure we understood the basics, since we're using those basics throughout the rest of the chapters. For chapter 2, there's just 1 homework assignment. So we're covering the entire chapter this week, 1 homework assignment. Our next exam is on both chapter 2 and 3. Okay, so 3 is a little bit longer, a little more intensive, so we'll spend more than a week on chapter 3. Chapter 2, a lot of it is just familiarizing ourselves with the periodic table. Okay, and a lot of that information and deep description you'll get off the PowerPoint videos. So for this week, what you're going to have available to you is there are 2 parts of the chapter 2 PowerPoints. I split it into 2 parts just because that way it's not too long, so you can watch one about 40 minutes and the other I think is about 30. So you can watch one at the beginning of the week and then one towards the middle, okay, just to kind of break it up a little bit. And then there should be, by the end of the week, all 3 class videos up. So I try to get them posted at least that day. So today's video should be posted by tonight. It just sometimes takes a little later into the night when I have a chance to upload everything and convert it and all that. So, all right. There's also a folder. So this is all in the week 4 folder. Inside that folder, there's another folder that says videos. Those are supplemental videos. Okay, so they are per topic. So for instance, one of the topics we're talking about in chapter 2 is electron configuration. So there's a video of someone else explaining it on just that topic. Just in case you're not getting how I'm explaining it, I like to try to add extra videos that other students have found helpful in the past. So feel free to delve into that if there's a topic that you're not understanding. There's quite a few videos in that folder you can use. All right, so now we're going to get started. I'm going to shut the door just in case there's some cut down on background noise. So in the PowerPoint, it'll get more descriptive, but I do want to start with the structure of an atom. Which has 3 subatomic particles. So I want to introduce it this way is because we're going to be calculating these 3 subatomic particles using nuclide symbols and some other representations of isotopes. But, so when you're looking at an atom, you have the nucleus, which is the center. So that's going to be my blue sphere here. Inside the nucleus, you're going to have P pluses, which are called protons. And you're going to have N sub 0, which are neutrons. Okay, so these are just shorthand symbols. So that for neutrons, I want to have it better read because that red is not very good. Let's see if this works better. It does. Protons. And then the last subatomic particle we're going to talk about are the electrons. And the electrons are not in the nucleus. Okay? They're on these surrounding energy levels. So we have little guys on all levels. Okay, and these are the electrons represented by this E- sign. All right, so this is just one of the ways an atom is represented. Okay, there's several other ways, but the things that remain in common is you have the protons and neutrons, so those are 2 of the 3 subatomic particles present in the nucleus. Okay, so these 2 guys are in the nucleus. They are also called nucleons for that reason. Surrounding the nucleus, in these outer orbital levels, and we'll talk about what an orbital is later, are electrons. So that's the 3rd subatomic particle. what you need to know about these particles are their charges and their masses. Oh, dang it. All right. The periodic table just fell for people who couldn't see. We tried taping it up. So you guys virtually will have to watch the video to look at the periodic table. All right, so getting back to the charges, sorry. So neutrons are neutral. So that means they have a 0 charge. That's why they're represented by this N sub-0. I guess it's not sub-0. But protons, notice they have a plus, so they have a +1 charge. Electrons, -1 charge. So notice, in the nucleus, we have neutrons and protons. So the neutrons are neutrally charged, hence the name, 0. Protons are positively charged, so that means the nucleus itself is positive overall. Because a positive plus a neutral charge is going to equal positive. So this positive center, the reason the electrons are orbiting it is because opposites attract. Electrons have a negative charge. This nucleus has a positive charge. So this causes the electrons to be attracted to that nucleus, and that's why they're orbiting it. That's why they're close to it. Okay, well now let's look at masses. So for mass, for our purposes, we're going to say neutrons have a mass of 1. The units on that is AMU. It's atomic mass units. It's a made-up unit. So you don't need to put the units on it. Okay, we're just going to label it as 1. If you want to, you can write AMU, atomic mass units. Protons also worth 1. Nice whole numbers. This is going to help us because we're going to be calculating these in a minute. The electrons, they do have a very, very small mass. It's like 0.005 something. Okay, or I think there might be more zeros than that. But for our purposes, electrons are going to have 0 mass. So the reason we want to know about masses is because we're about to calculate the mass number of specific atoms. And when we're counting mass number, we want to make sure we're only taking into account how many protons and how many neutrons that atom has. We're not going to worry about how many electrons when it comes to mass. Okay? So for mass, neutrons and protons. If we look at charges, which we will later on in the chapter, probably not today, we're going to focus on protons and electrons. Notice neutrons don't have a charge. So when we talk about charge, we're going to ignore neutrons and just look at protons and electrons. Okay? Questions so far? Eraser? All right, so with that, I'll give you a definition. Anyone heard of isotopes before? Okay, so what isotopes are, they're atoms. So here's our picture of an atom, right? Of the same element with different mass numbers. Okay. So if they differ in mass number, what that means is they have a different number of neutrons. Because mass number is protons plus neutrons, right? We said those are the only 2 subatomic particles with a mass of 1 each that count. Now, why is it the neutrons that change and not the protons? Protons of a specific element will never change. Protons give the identity of that element. Okay, for instance, hydrogen. If you look at the periodic table I handed out to you, it's the first one on the periodic table, 1. That 1 is how many protons it has. So all atoms of hydrogen have 1 proton all the time, no matter what. Their neutrons can change, their protons cannot. If I change the number of protons, say I say 2 protons, well, I'm not talking about hydrogen anymore. Now I moved over to helium, because helium's number 2. So for the people in class, the blue numbers on this periodic table, those are the number of protons of every element on the periodic table, and those will never change. If they do, you're changing the identity of the element. Okay, so the neutrons is what differs. So let's look at an example of isotopes, so we can see how this looks. I'll leave that up there. So Isotopes can be represented in two ways. One way is by a nuclide symbol. And that's where we have the element symbol represented where that letter X is. And then up here, we have a mass number. And down in the lower left, this is the number of protons, also known as the atomic number. Okay, those numbers in blue. The other way to represent an isotope is by writing the element name dash and then mass number. All right, so what I'm going to do over here is I'm going to write some nuclide symbols of a pair of isotopes, and we're going to calculate the protons, neutrons, and electrons present in those. Okay, so bromine has two isotopes. So isotopes are atoms of the same element with different mass numbers. So we're talking about two different atoms of bromine, and they differ by their mass number, because when we write nuclide symbols, the mass number is this number up here. And notice that number is different between the two. One is bromine 79, one is bromine 81. I said the number of protons would be down here. A lot of times when they write nuclide symbols, they don't include the number of protons. Why? You can use your periodic table to figure it out. So for the people following along virtually, you might want to get that periodic table in the week 4 folder out. The same one we're using here. So if you find bromine on the periodic table, you'll see it's number 35. Since it's number 35, that means it has 35 protons. Okay, so if they don't give you that number, that's okay, because you know where to look for it. You can just find the symbol on here and write down the number of protons. So I'm going to write 35 here and here. Notice protons always stay the same when we're talking about the same element. It's the mass number that differs. All right, so let's calculate protons, neutrons, electrons for both of these and see how they are the same and how they are different. So these are the 3 subatomic particles in an atom. So protons, how many protons does bromine have? That's the 35. That's the number that's not going to change. So it doesn't matter if I'm talking about the isotope with a mass number of 81 or the isotope with a mass number of 79. Their protons are going to stay the same. So I'm going to put it the same on both of these. What's different between these two isotopes is the neutrons. So we should see different numbers here. How do we calculate it? We're going to subtract, right? This is the equation for mass number. It's the protons and the neutrons. So if we rearrange this to solve for neutrons, we're going to be taking the mass number and we're going to subtract the number of protons. Right, I just subtracted protons from both sides. So the nice thing about nuclide symbols is they line up perfect for you to do that. This is my mass number. This is my protons. So just draw a line there and a subtraction sign. 81 minus 35, I have no idea because I'm using what math in my head.
46.
46, thank you. So subtracting those two numbers gives me 46. Notice if you add these two, it should equal the mass number. Mass numbers are always whole numbers. Okay. So neutrons for a different isotope of the same atom should be different. So once again, we're subtracting those two. 44 this time. And adding those should give you 79. Now for the electrons, we haven't talked about this yet. Well, with nuclide symbols, if there's a charge, and I don't think we're going to ever see one in this class, but just so you know, if there's a charge, it's going to be up here. We'll see charges eventually, but we won't see them with nuclide symbols specifically, okay? So you'll see it here. So if there's nothing here, if there's not a plus sign here or a minus sign here, that means it's neutral. That means it has no charge. So if it's neutral, that means the protons have to equal what?
Electrons.
Electrons. Protons have a +1 charge. Electrons have a -1 charge. So we need the same amount of both so they cancel each other out so we get an overall neutral atom. So if you know the protons, it's going to be the same electrons. Okay, so we have 35 for both. We're going to try 2 more examples, but instead of writing it like a nuclide symbol, we're going to write it in the other representation. So isotopes can be represented both of these ways, as a nuclide symbol, what we just looked at, or by writing the element name dash mass number. So let's do one of those. Which ones did I write down? Iron.
Chlorine.
Is that right? Oh, I guess it is. And then chlorine 37. And I did some different ones on the PowerPoint, I think. I can't remember if I gave the answer numbers or not.
No,
I didn't?
not on these.
I was trying to do different ones so that I didn't give the answers away on the PowerPoints in case you watched them before you came, so you can try new ones. All right, so I'm going to erase this part so we have some room. And we're going to do a couple different things. We're going to calculate, so we'll start with iron 57. I'll put him up here. The protons, neutrons, electrons for him. But we're also going to change this and write it in a nuclide symbol form instead, just to get practice with it, so we can helps us recognize it better. All right, so iron 57, remember, this dash 57, this is the mass number. Okay, so this is not the number of protons, that's a common mistake. That's the total mass number, that's the protons plus the neutrons. So how do we figure out how many protons iron has? Periodic table. What number is it? It's 26, it's Fe. I don't know why I can't see it. There it is. So 26. Okay. For the neutrons, how do we figure that out? Oh, so you're looking at electrons because you said that they have a charge. So yeah, let's do electrons first. That's the easier one, right? Whenever we write a isotope in this format, it's going to be neutral because there's no way to write it as a charge when it's written this way. So you can assume it's neutral whenever it's written by element name dash mass number. So that would mean that your electrons are going to be the same. So let's do electrons first since that one's the same. Neutrons, we have some calculations to do. So what 2 numbers are we subtracting? 57 minus 26, right. Taking the mass number 57, subtracting out the protons, 26. What did you get?
31.
31. That one I might have been able to do in my head.
Just, it's early.
It is, well, yeah. I'd rather just have someone actually do it and get it right first instead of me mess up on camera. It's great age we live in. Everything's recorded now. All right, so we're not done because I said we're going to put it as a nuclide symbol. So how does that look? Well, what's the symbol? So X, what's the symbol for iron?
Fe.
Fe. What's going to go up here in this upper left?
Mass.
Mass number, so 57. And then you can, but you don't have to put the number of protons here. This can be omitted. But if you want to include it, make sure you're putting the protons, not the neutrons there. Okay, but if it's not there, that's still correct. I want to point out something quick while we have this symbol up, is that nuclide symbols are different than how the periodic table represents the element. So on the periodic table, we have iron, but notice our protons are up here instead of in the lower left corner. So protons are always on top when you're looking at them in the periodic table. Also, the number is 55.85. This is average atomic mass. So on the periodic table, the mass they give you is not a whole number because it's different than mass number. So what this average atomic mass is it's an average of all the isotopes of iron. Because iron has more than one isotope. Iron 57 is just one of them. Iron 55 would be another one. Okay? So dependent upon their abundance on Earth, they take all of the iron atoms out there, calculate their natural abundance, and get an average atomic mass. If you want to know how to calculate that, get with me on our own time, because you don't have to know how to do that for this course. So I'm going to skip the calculation part. It is kind of cool, but you have to know their abundances and all of that in order to calculate it. So I just want to point out that they are represented differently. So this is periodic table version, and then this is nuclide symbol representing one of the isotopes of iron. All right. So let's do one more, and I'll see if there's questions, and if there's not, we'll move on to the next topic. So we're going to do this Quern 37 now. All right, so protons, neutrons, electrons. Go ahead.
Protons is 17.
17. Yep.
Electrons is 17, and neutrons is 20.
You said electrons was 17?
There's no charge.
Okay, that makes sense because it's neutral, and then neutrons were
20.
20. So how'd you get the neutrons?
Subtract 37 from 17.
Right.
With 17 from 37.
Yeah, 37 minus 17 gives you 20. Good. All right. How about the nuclide symbol? What's the symbol for Quern? L. What number goes in the upper left?
37.
37, and you can stop there, but if you don't, what number is going to go down here?
17.
17. So that's the atomic number being the same thing as the number of protons. Okay, you might hear both terms. Atomic number is the number of protons. All right, questions on this? All right. We're going to look then at some special groups on the periodic table. So for the virtual people, fast forward. Because we're going to be looking at the periodic tables in front of us, and I'm going to be pointing to one off to the side that you probably won't be able to see. And we'll talk more about the arrangement of the periodic table when we talk about Dmitri Mendeleev, who came up with the original version of the periodic table. I think that's the second half of this chapter. But for now, what I want to point out are a couple different things. What we're going to be using this next section for is if you are given an element, you need to be able to tell me if it's a metal, if it's a non-metal, if it's a metalloid. You also need to be able, if it's in our particular special group, to tell me what special group it's in. Okay, so I'm just going to write a few of the elements here. We have hydrogen here, and helium. Oxygen, fluorine, and neon. So just so you get an idea of what the areas are, I'm just going to write the first row. Okay, so what do we need to know about the periodic table? Well, first off, these two columns here, these two groups, and then these 6, these are called the representative or main group elements. And if you're using that periodic table from Blackboard, it says representative elements and has already labeled it for you. Okay? So these main group representative elements, we're going to know a lot about these. We're going to be able to figure out how many valence electrons are in each. We're going to be able to figure out their electron configurations, what their charges always are, just by where they are on the periodic table. Okay, so we'll focus on them quite a bit. The middle guys here are the transition elements, also known as transition metals, because they are all metals. So now for the special groups. Group 1, And by group, I'm talking about up and down a column, okay? So the reason that the periodic table is represented in groups is because similar groups have similar properties. So as you go down a column, all the elements in that column for the main group metals, not the transition metals, have similar properties. Okay, so for this first group, and when I'm talking about this first group, I'm not including hydrogen. Hydrogen is a being of its own. Okay, so I'm talking about lithium on down. So lithium, sodium, potassium, rubidium, cesium, all those. This first group is called the alkali metals. So if I give you any one of those elements and say, what group is it in, you need to be able to tell me. Okay, so it's a good idea to probably just label these on the periodic table you have. That way you'll be seeing them all the time when you're looking at the periodic table and they'll stick in your head. So the next group, group 2, starting with beryllium on down, that is the alkaline earth. Those are also metals, alkaline earth metals. Okay, the D block, this whole center section, and you'll see what I mean about D block in a moment. These are the transition metals, so anything in there, you just call it a transition metal. Okay. The next few groups. So when I'm talking about groups, notice boron, if you look above boron, it says 3A, and then in parentheses it says 13. Okay, so the nice thing about this periodic table is it gives you every possible label that you'll see on any periodic table. Some periodic tables call that group where boron is on down just 13. Some of them call it by 3A. This one gives you both options, so no matter what question or what book you're reading, you'll know what they're talking about because it has all the possible labels you'll see for that group. So this group is known as 3A or group 13. It doesn't have a special name. And you'll see why in a minute. It's actually because the elements in this group don't have similar properties, so they're not given a special name. Because some of these guys are nonmetals. Some are going to be semi-metals and some are going to be metals. So it's a hodgepodge group. Where carbon is, that's going to be called group 4A or group 14. That also does not have a special name. Same reason. It's got a combination of metals, nonmetals, metalloids. Same for nitrogen's group and oxygen's group. So nitrogen on down is 5A or 15. Oxygen on down is 6A or 16. So we're skipping those guys, and once we get to fluorine, so fluorine, chlorine, bromine, iodine, those do have a special name. They are all nonmetals, and they are called the halogens. So if I give you an element in that group, I don't want you telling me that it's group 7A. I want you giving me the common name when you can. If the group I'm talking about does not have a common name, then you can give me the 3A or the 13, 5A, 15, that sort of thing.
I have a question.
Yes?
You said all of them in a row was non-metal? So we got,
Yes.
so
Well, except right after iodine's not. You're right. I missed that. So iodine's the last one. Astatine is semi-metal because it's along that zigzag line.
okay, I was just making sure I didn't mess up.
No, you didn't. So this very last one she was just pointing out, astatine with the A, S, this is actually a metalloid. And we're going to look at where those are in a minute. All right, last group, noble gases. So these are the cool kids at the table. Everybody wants to be a noble gas. We'll talk more about that later on in this chapter as well. So with that, we now have our special groups. So there's basically 5 that you need to remember, and then the rest you can label based off of the numbers that are above that group. Now let's look at metals, nonmetals, and metalloids. So there's a zigzag line on the periodic table, and you have one present on the one in front of you. It's just a darker line that kind of goes down like this. Keep in mind I'm not an artist, so that's going to be different looking than yours. Working with what I got here. So this zigzag line, what's important about it is it's separating the periodic table into metals. So metals are all to the left of that zigzag line. and nonmetals. And the nonmetals are all to the right. So notice there's only a few nonmetals in comparison to metals. But more important thing is everything touching this zigzag line, except for aluminum, which of course there's always got to be an exception. You'll see that in this course. There's about a zillion of them. So aluminum is a metal, but everything else on that zigzag line are called nonmetals. So silicon, germanium, arsenic, antimony, beryllium, polonium, and then astatine. Those are all metalloids. The other name for that is semi-metal, so it means the same thing. This guy here is a metalloid. Okay, so let's do a few examples. I'm going to write the symbols. Oh, that's a tricky one because I didn't tell you about him yet. And we're going to label them as metals, nonmetals, metalloids. And then if they're in a special group, we'll put the name. If they're not in a special group, we'll just put the group number they're in. So fluorine, F. It's a nonmetal. And what's the special group? It has a name, so we don't want to put 17.
Yeah.
So it's in the halogen group. So if it has a special name, use it. If it doesn't, then use the number. Okay, hydrogen, we didn't talk about him. We just said he was all on his own. Do you think hydrogen's a nonmetal, metalloid, or a metal? So it's tricky because notice hydrogen is right. It's in the same group as the alkali metals, but it's actually not a metal. It's a nonmetal. It belongs over here next to helium in that case. So hydrogen is a nonmetal. It does not have a special group name because even though it's in the same group as the alkali metals, it is not an alkali metal. So we would say hydrogen is just group 1 or group 1A. Your choice. Let's try strontium. What number is strontium?
38.
38. So if you're looking at your periodic table, it's number 38. So it's got 38 protons. But what is it? A metal, a nonmetal, or a metalloid? Metal, yes, because it's in group 2. Alkaline earth, yes. So it does have a special name because it's in group 2 there. So alkaline earth. So K. Now K is actually potassium, so its symbol does not match up with what you think it should be. What number is potassium, whoever finds it first? How many protons does it have?
19.
19? Yep, it's number 19. So what group is it in? Yep, so it's alkali, so it's the first group. Not alkaline earth, but alkali, and then it's a metal. Because remember, everything to the left of that zigzag line is a metal. How about krypton? Kr.
36 is a noble gas.
Noble gas, number 36, is in this last group here. And so is it a metal, non-metal, or metalloid? Non-metal. So pretty much, I think everything in that group is a non-metal. All the way down to Rita? Yeah. That one works. Oops, can't spell. I'm just going to put non. Do one more for fun. AU. You don't know what AU is? It is gold. What number is it? How many protons does it have?
79.
79. So, is it a metal? Is gold a metal?
Yeah.
I mean, that's one you should already know without even having to look at the periodic table. Does it have a special group name?
No.
It's 79. It does have a special group name because it's in this
So the
section.
transitional metals.
So we would call it a transition metal. Yes. Is everyone seeing kind of how we would use the organization? You would be given a name or a symbol, and you'd have to tell metal, non-metal, metalloid, or special group name. And if it doesn't have a special group name, just use the heading. Group 1, Group 1A, Group 13, Group 3A. Anything like that. All right. So now that I have this still written up here, we're going to start looking at electron configuration next. Okay, electron configuration is a confusing topic at first. Once you get the hang of it, you might even find it fun though. Then again, I'm me and find things like this fun. But, so when you're watching the PowerPoints, I'm going to discuss a little bit in detail about some quantum numbers. So this is physical chemistry. That's one of the hardest chemistries, but we're just brushing the surface, okay? So we're going to be talking about principal quantum numbers, all right? So the principal quantum number is just a big word for the numbers that you see on the side of the periodic table, for the rows. Okay, so if you're looking at your periodic table, you'll see there's numbers by each row. How many rows is there? 7, right? 4. So these are the principal quantum numbers. So if you're given an element, say I give you nitrogen, and I say, what principal quantum number do I have to look at to find nitrogen? Let's see, nitrogen's in row 2, so its principal quantum number is 2. Okay, so you're just following rows now instead of columns. Okay, so principal quantum numbers, those are the numbers off to the side here. What we're going to look at next is angular momentum quantum number. So I'm going to use a different color for that. Okay, these are going to be my S's, my P's, my D's. There's also F's, but F's are the lactonides and actinides way down here, so we're going to ignore those for now. So basically what we're doing with these quantum numbers is we're trying to figure out the electron configuration of an atom. What that means is how many electrons does it have and where are they? Okay, because when we looked at the structure of an atom before, remember I said you have this nucleus and then the electrons were somewhere on one of these orbiting circles. Okay, and so what we're trying to do with electron configuration is describe these electrons and where they are. So the principal quantum numbers off to the side there, that represents these circles. Okay, so what I mean by that is this first ring, this would be n equals 1. So we're looking at an electron in one of those groups. Okay, this next one would be n equals 2. And then the third one, n equals 3, so on and so forth. Okay, so the further down you go, the more shells that you're going to have around that atom. And we'll actually see that the further down you go, the larger the atoms themselves are. So for instance, cesium, who is this guy right in this bottom corner. Well, actually francium's there, but he's radioactive, so we're going to look at cesium. Cesium is the largest atom on the periodic table for this very reason, because it has so many shells. It has principal quantum number of 6, right? Sure I'm saying that right? It is 6, yes. So because of all those shells, it's very large. All right? So notice the principal quantum number, it just tells us what circle, what orbit to look in. So we need to narrow that down further. So to narrow that down further, we're looking at the angular momentum quantum number. So what that's going to tell us is approximate area on that ring where the electron is. Okay? We can't pinpoint electrons exactly because they're constantly moving, but we can figure out the probability of the area they're in. Like they're probably in this area most likely. So this next section is going to help us figure that out. So when we apply it to the periodic table, we have S, P, and D. So these are called sublevels. So the S sublevel are these two columns here. Okay, so alkali metals and alkaline earth, they are our S block is what we're going to call them. So if I say, okay, it is in the 2s block, what that means is it's printable quantum number 2 and it's in the S block. So it's going to be one of these two elements. Okay, so I'm just trying to narrow down where to look. Well, what if I say 2p, because p is another one of these angular momentum quantum numbers. Well, I would know it's group 2, but then I'd need to know where the p's are. So where are the p's? They're over here. They're the rest of the main group elements. They're not 2, but this is the P block, I would call it. Okay, so that main group elements over here, the 6, from boron all the way to the noble gases. We only have one letter left. Where do you think that's at? The transition metals, the D block. I think I referred to it as the D block when we first looked at it. And that's the reason why, because these are the D block. Notice I said we're going to try to use this to figure out specific elements. Okay? Well, knowing it's in the 5D, that just gives us a range of several different ones. So we need to narrow it down even further. Okay? So we'll do that next time, but I want to leave you with the possibilities in each of these blocks. What I mean by that, the S block. Notice that there's just 2 columns. So that means it has a max of 2 electrons. Just remember, we're using this to describe electrons. We can only have 1 electron in each column. So 1, 2. How about the D block? How many are present in the D block when you count elements all the way across? What's its max? 10. So that means it can have a max of 10 electrons. What about the P block? 6. Okay, so we're going to be using this knowledge, these maxes, to figure out electron configurations for all neutral elements on the periodic table. Okay, so we'll practice with this. Once we get it for neutral elements, we're going to look at charged elements. Okay, so for the S block, we said max of 2 electrons, and it actually has 1 orbital. And what an orbital is it's that probability region of where an electron is. And each orbital can only hold a max of 2 electrons. Okay, so if the S can only hold a max of 2, that means it can only have 1 orbital. Okay, well, the P, we said, could have a max of 6 electrons. So how many orbitals do you think it has, since each orbital can hold 2? 3. So we have 3 orbitals. And if you look at the PowerPoints, you can actually see pictures of these orbitals. So S, P, and D all look a little different. Last but not least, we said 10 electrons according to the periodic table. So how many orbitals would the D block? 5. All right, so we're going to end with this, and when we come back on Wednesday, or when you watch the video on Wednesday, whether you're here or not, we're going to be using a combination of the principal quantum numbers and letters and numbers to represent these as electron configurations. So you watch the video to kind of get an idea of it before you, and by the video I mean the PowerPoint video, before you watch the video on Wednesday. It might help you understand it better. Okay, so we'll be doing that and then moving on to part 2 of the PowerPoint videos. So that's all I have for you today. Apparently I need stronger tape if I'm going to use that. My picture wasn't that bad though, right? It was easy to